Hello, everyone. Today we will solve problem number 44 in deepml.com, which is leaky rectified linear unit activation function. I'm going to do something that's different from the previous videos. I'm just going to show you the solution code right from the get-go, and then I'll talk about what this function is, why do we care, and why this code is so simple. So this code is very straightforward. It's almost the same as the one in the previous video about the ReLU function, with the main difference that instead of having maximum of 0 and C, now we're going to have maximum of alpha times C and C. So we're going to submit the code. And after we wait a little bit, we'll see that all of the test cases are accepted. So that's great. That's the solution. Now we're going to figure out why do we care about that. So let's think about what the ReLU function was. And I highly recommend that you watch the previous video if you haven't watched it yet, as there's some concepts over there that I'm going to introduce. And I'm going to assume that you already saw it. So the ReLU function, as you may remember, looked like this green line over here. And so we talked previously about the main problem of the ReLU function, which is, let's say your data looked like this, all of these blue dots over here. So let's say this was the pattern of the actual data, something like that, maybe, whatever. The main problem with the ReLU function is that for every single value of x that's lower than 0, the function is going to flatten them. So all of these blue points are going to get flattened towards the x-axis. Now you may be wondering, well, why is that a problem? The whole point of neural networks and all of the other machine learning techniques is that we try to figure out patterns from the data, and we try to identify them the best we can. So when you're doing this, you're actually losing a lot of information. Why? Because there's this sine wave pattern for all of the negative input values, which are going to be squished. It's as if they didn't exist. And so your fit is not going to be as good as it could otherwise be. Now, I said that, well, that was the problem with the ReLU function. And now this other thing, Leaky ReLU, came to save the day. So let's remember that ReLU function, as I said before, is simply the maximum between 0 and an input, which we're going to call x. So now the evolution of that is what's called the Leaky ReLU function, which is instead of taking the maximum between 0 and x, we're taking the maximum between alpha times x and x, where alpha is a positive number that is going to be one of the hyperparameters of your model. That's something that you have to figure out. And so what's the benefit of this? Well, instead of having this flattening over here, you're going to have something like this. So you're also going to have a line here, and then it's going to continue in this direction. Both of these lines should be the same. I'm just drawing them side by side so you can see that both of them are there, but the gist of it is that they should be together. So what's the big deal? This is obviously not a very good fit, right? Well, the main difference is that remember that when you're thinking about neural networks, you have a lot of layers. So you would have something like, here's the input, and it goes to a layer, and it goes to another layer, and so on and so forth, until you get to the output. So if you were using the ReLU function, what would happen here is that, let's say you have a negative number, then it would get flattened. And so this 0, this flattening of the negative number, would propagate throughout the whole network. Whereas here, instead of flattening it to 0, you're just reducing its magnitude. It's going to be somewhat smaller, right? But it's not going to be 0. It's going to be a number. It's going to be this thing, maybe. And so when you pass it along, when you multiply with all the matrices and you add the bias terms and so on and so forth, this term is not going to be 0. It's going to be something different from 0, more likely than not. Whereas here, it's also going to be 0. So the main difference is that by having the Leaky ReLU, you prevent that value from being shut off. That is, the value is going to keep propagating towards the network, and it can give some information to your model about what the actual pattern underlying the data is. That's opposed to the ReLU function, in which everything just gets flattened and it's almost as if it didn't exist. So that's why we have the Leaky ReLU function, and that's why we should care about it. Now, in production, you may see the Leaky ReLU function more than the ReLU function. One of the main drawbacks of the Leaky ReLU function is that you now have to estimate what would be the best value of alpha, this thing over here. Because you can come up with any number. In this problem, we were given a number that was 0.01, but that may not be the best one for your data. And there's no way of knowing ex ante. You just have to try and get a lot of experience and figure out which one fits your data best without falling into overfitting. But that's the gist of it. That's the main idea. And that's why we code out this function. As you see, both of these problems are very straightforward, but they have a lot of implications of, it's interesting to understand not only how you can code it, which is super straightforward, as I already said, but why it is that we're coding them and what's their use in machine learning projects. So thank you for your attention and hope to see you on the next one.